So let's wait a bit while people come back. And so yeah, you shared with me that you have been living half of year in complete happiness about solution you have found with your professor until you found out that the solution has been invented already previously, right?
Exactly. I think it's actually a very common case in all science that people tend to reinvent something because they don't know that something exists, and we also fail this trap. So we invented a Fisher test for a three-way interaction, which is a kind of extension of two-way interaction test. And then it appeared that this test has been already created. It's a hard psychologically moment. And we went around bragging about it also. I mean, I did, not the professor. So turned out some employment opportunities.
But you didn't discover it previously just because it was your mistake that you didn't look properly, or it was hard to find it, or what?
Yeah, it was quite hard to spot because first of all, it's quite a narrow niche. And the second, this publication that had it introduced for the first time, it was in a quite low impact factor journal, which means that we somehow just after, we of course researched a lot, but somehow after some time we just found it, that it was there.
I feel for you.
Yeah, thanks.
But it has been only once or several times?
No, it has been twice actually.
Twice.
But the first one was even more fun because it was still in university years. I thought I invented theoretically a material that allows transmission of ultrasonic waves almost without loss. But I found that a derivative is able to find either minimum or maximum. I mean, it is zero either in minimum or maximum. So after it appeared that it was material with the least transmission properties, not the most. Yeah.
Yeah. So, and you haven't made your conclusions that it's better to go away from science, yeah?
Sorry?
I'm joking. I'm joking that you haven't made the right conclusions that don't mess with science, go away and just do simple stuff. You still.
Yeah, that's true. That's true. Still, I like miss it very much, and I think I kind of do it in via data without publication in journals.
I see. No, I think maybe it's good. Maybe it's enough for chatting right now. Maybe let's switch to your presentation. Can you share your screen?
Yes, sure.
Well, you also haven't given us feedback about Agnes' presentation. Please go to the link and do it. Nice. And I will drop link to another link for Dmitry's presentation for feedback later at the end of the presentation. So, okay, then Dmitry, you are ready, right?
Yes.
Then stage is yours. You are welcome.
Thank you. Thank you. So, hi everyone. My name is Dmitry Lvov. I am head of risk in a fintech company called VIASMS Group. And the company issues loans, cards, it does payments and investments. So during today's talk, I'd like to tell you about what we have created during some 5 to 6 years in terms of automatic machine learning and the structure. Yes, by the way, I have seen a lot of some names of my friends, familiar people. So hi everyone who I know. So the outline of the presentation is following. First, we'll start learning how the credit business works in fintech and in banks. Then why machine learning is needed, beneficial, and also why automated machine learning. And after that, we will dig into details of getting data, building models, evaluating them, deploying, and monitoring. So this is how a bank works. So in the middle, there is a bank, and to the left, I hope it's for you also to the left and not mirrored. There are other banks that give loans to that bank, and there are also customers who bring money to the bank. And both parties in our world, in our times, they pay about 0%. They receive about 0% interest, so money is almost free. And a bank would issue a loan on quite different conditions. For example, a mortgage loan for a flat would have an APR, which is an annual percentage rate of about 3% currently in Latvia. And consumer loans differ wildly, and what is stated on banks' pages is something between 10 and 50%. So here we see that the loans with collateral are much less expensive, and that is of course due to the fact that if such loan is not being returned, the collateral, which is a flat or a car, probably flat at this rate, will get sold or somehow liquidated in another way, and the bank doesn't suffer loss or suffers little loss. So in fintech, there are many companies, I'm sure you know all them. Credit business works the same way. There is a fintech lender. It grants loans, historically more expensive loans, which is currently being changed by a regulator all the time. So current APR is almost equal to the bank's maximum APR. These loans are getting published on platforms such as Mintos, VIASMS, and then private individuals and companies come to those platforms and invest in those loans. Or think to a classic bank. So after the loan has been issued, a fintech or a bank assumes it will make some revenue, and this revenue is like the height of this column. And of course, it's very different from profit. So in order to get the profit, we must subtract the cost of non-performing loans, the defaults, the loans that are not being paid back, operational cost, like all the things related to issuing the loan and administration and the salaries of data scientists and so on, and the cost of funds, of course. So we can dramatically impact the red and the yellow things. So we can issue, if we have a good enough models, we can only issue loans to customers who are able and willing to repay them. And we can reduce the red thing if we do all this underwriting work automatically without the manual work of the operator. So why ML at fintech? Yes, the average loan amounts are much lower. For example, in fintech, according to the Association of non-bank lenders, the average is around 500 euros. And in the bank, average consumer loan is threefold, it's 1.5 according to Bank of Latvia. So that means that even given the same interest, the amount of money that can be spent on manual work is much less in fintech. There are also much less strict rules in fintech as compared to banks. For example, I know some banks do not issue loans only if there is a fact of using fintech loans in the customer. Or there is a rejection for a loan because there was a fine, unpaid fine somewhere, maybe somebody already forgot it in the past. So usually there are no such strict rules, and the goal is to calculate the true risk of a customer being not able or not willing to repay. So reason two, it must be calculated as precisely as possible. And the third one is that the regulation and bureaucracy are quite low. Also, there are no old legacy systems that are there for 50 years. And basically, these companies are, because of this, in good position to use the newest black box algorithms that are out of the box. They provide quite good accuracies. And so I think almost every fintech uses such algorithms nowadays. Whereas in the banks, scorecards are sometimes described by text in documentations and policies or procedures. So, and why AutoML? Main benefits that we found are the same, actually, well, very similar to the benefits of IT, code-based management, and these are the singular across the whole team. And the team, of course, changes sometimes. People grow and find opportunities elsewhere. But if there is a single repository, their work remains and is accessible to new guys. So there is also a don't repeat yourself benefit that each time you're building a model, you don't need to write all the auxiliary code from scratch or find it across different files. So fast turnaround of models is required because regulations change. So each change of regulations often leads to different conditions for customers or to different data available about customers. And we are able, thanks to automatic machine learning, to respond to these changes fast. All right, also we have this strategy of using exactly the same code of processing data and during prediction. And I think it creates quite a good economy in terms of time to production. And it's just more fun because you are working on something big, seemingly big, and it grows and gets better and so on. So this is the usual life cycle, quite simple, or maybe simplified, and it contains of 4 main blocks. So we need to get the data. Unlike in Kaggle, the data is not there. So our strategy for data getting is like sprouting across all the possible internal and external databases in search of data. Then there is training, evaluation, and deployment. So for training, even if it's second or in this diagram, I would like to start with that one, because it actually appeared that in order to get a good enough model, it is much more important to work on the data than on training. So training was actually a bit easier, maybe. So the goal of training is to train the model and ensure it is performing and it's not overfit, and it contains of splitting data into train test, hyperparameter tuning using existing package. It's available in R and in Python. Cross-validation to check results, and some auxiliary code also to cache the intermediate results, because sometimes training can, both training and data preparation can take a lot of time, and therefore there is a need of caching, saving. And the message here is that in our world there is such a great collection of packages that are existent, like these carrot packages and many more, which are just plug and play. And the task of implementing machine learning in production actually becomes a lot an IT task. So this is it for training. Now getting data. So the goal is to download and transform the dataset so it can be consumed by an existing advanced algorithm. Speaking of algorithms, they are forests and extreme gradient boosting usually. So this code that does all this is roughly 1,000 rows of SQL in different files, and it is being used to get data from more than 10 internal databases. So there are two very different strategies of building model APIs. One expects all the atomic fields as inputs, but the other one, and that we chose, is that we only expect an identifier of a client, and then all the sprouting work gets done by this pipeline code. So there are 20 various, we call them attachers, thanks to one of the colleagues who has invented such concept. And these are used to convert specific data into a format that is consumable by machine learning algorithm. So an example of such data could be an email. I know of a company called Frogster who is using extracting 60 different variables from an email, such as well, the easiest are, of course, the major domain address and the main address, and whether this first part of email tells us something meaningful, and so on. So there are also bank statements, credit bureau data, and even Google Analytics. There is also a type information. I mean model type. Some models require that all character values are dumized. Some models want only numeric data as input, so there is a dumization step of columns that have very little unique values, and also outlier processing. Then in the pipeline, types are encoded with prefixes, and oops, sorry, it was supposed to be in different place. I'm sure you heard that in data science it's 20% machine learning and 80% working with data. So here is a snapshot from GitLab of our machine learning repository, and it shows that around 70% of the code is actually SQL, which means data processing and feature engineering and so on, and only 30 is R code. So after we converted all these complex data types to simple types, and simple types are character, numeric, or NAs, and the important part is that all the code being written and proven to work, all the code ends up in production for serving. So for these simple fields, for characters, we convert the encoding, make them same case, demise, and drop prevalent, as I already told that. For numeric, we must ensure that they are numeric and drop outliers. And for NAs, depending on the algorithm, either make numeric in a very extreme range, or some algorithms actually allow NAs, and then it's not a problem. So the attachers. The attachers work with some specific. The attachers are at the next level of complexity compared to these transformers. So attachers, they can take, for example, a date as input, and from that date, they can create lots and lots of different algorithms, data features. For example, each fed into this processing pipeline can have day, month, hour, and so on extracted. And I know of some more exotic, like the moon phase, you know, some people I have seen using these more exotic ways to feature engineering. So for the text, we tokenize everything, meaning that if there is a sentence as input, we just create a set of columns for each word. For email, like extract information. For sequence of fields, we get the slope. For example, a sequence could be the history of previous loan applications, or a history of previous overdue loans. All right. So, and the complexity also is that every market, and we are present in 8 markets, they have 2 to 5 external sources, and new sources are being brought in, and all sources being retired. So this code is this repository of automated ML is a quite living organism. It always needs attention. And again, we reuse all this code from training. So for evaluation, and here I don't actually mean the evaluation during training, but a kind of a quality control evaluation. So after the model has been built, we evaluate it, and to do that, we predict out of time, like predict on values that happened in time later than the most recent point in training data. Then we run the champion, the current model, and we run challenger and compare both. And based on the results, propose thresholds for cutoffs. Next step is which is basically making the model available to consumption by other systems. And for us, every model is an API. And under that API, there is a Docker image with all the things that are necessary to serve it. We use an external vendor right now, but also have a backup version with our custom code, which is free, open source. And also to Kubernetes. And today I got the good news that our first model got into Kubernetes cluster. So I hope that it will allow us to serve even more stable in a more stable way. Okay, so then monitoring. We found that, well, in this using machine learning in production is a bit different from just building a models, because after you have built it, of course, you want to understand that the model still performs. And it is tempting very much to same metric that you used for training of the model, for example, ROC or AUC. And to us, it looks like it's actually wrong, because the decisions are being taken by that model, and there is a lot of, for example, loans that have been rejected, and we don't know anymore how their performance would look like. Should they be accepted? So it's a complex thing. It's called reject inference. There's a lot of papers on it, and nobody really seems to have a distinct answer on how to do it. We do the monitoring using some business metrics, like distributions of bad loans by score buckets, rolling default rates, and so on. So this is how the actual code looks in the end. This is everything that is needed to have a model in production. So first, find the data, do the attachers, then transform, then do the training, do deployment, quality checks, and thresholds. And this is it, basically. So what challenges we had? Most of them actually are related with quality control, and maintaining high quality code is really, really difficult, because data scientists and analysts and they have this excitement when they have introduced something new, some new data or new feature engineering approach or new algorithm, and they tend to try to put it in production as soon as possible. Therefore, the code, the first version usually looks like a mess, and it's one of most painful things. And in that sense, actually, folks who have experience with in IT and who write code, not machine learning, but some other programs, they usually tend to high quality code also in data science, which helps. It helps to get consistent results from time to time, of course, reduce bugs, and maintain. So data stability monitoring is challenging for us because usually it's a very good idea, and many companies are doing this. Usually it's useful to monitor each of the variables. But in our case of automated machine learning, we have sometimes hundreds and sometimes maybe thousands of variables. So even if we constantly check whether the distribution of these variables seems different from the training set, we get the multiple testing problems, and something that something that seems like having a big change actually doesn't, and it is there just for by chance. So because we use it in an automated way, and the black box algorithm is not interpretable, that is also one challenge that we need to solve, because sometimes it's extremely important to understand what actually was the data behind each calculated credit score. And one more thing is that we have not yet introduced, but are on the way, is to deploy the models straight from GitLab, which will basically mean that only tested code and the one from master branch would end up in production. Currently, this is manual. So we are hiring. If there was a spark of interest during this talk, or if you otherwise would like to try data science, or you are doing data science, machine learning, please reach me out. And otherwise, thank you very much for spending this evening not on the beach, but here on the internet. This is it. Thank you.